Welcome to lecture 27 of Machine Learning from Data. We're going to be talking about learning aids. So what are learning aids? So learning aids are additional tools, techniques that can be applied to all learning models that we have learned. Okay, linear models, RDF networks, support vector machines, neural networks, and whatever your favorite learning model is, you could use learning aids to help the performance. Okay, and they're relatively easy to implement. There's almost no downside, and so you can definitely use these techniques in practice to significantly improve, and in some cases, take a method that wouldn't work into a method that would work. Okay, now we will focus starting with input preprocessing. So how do you sort of account for arbitrary choices that could have been made during data collection? Okay, and essentially we'll be talking about techniques like input normalization. So algorithms that we develop typically expect the inputs in some standard form, and there's significant benefit to be gained from putting the inputs, the data, into that standard form. Then we'll move on to a famous technique called principal component analysis. Now, this can help in two ways. The first is it can reduce dimensions, and we know that lower dimension is better. Okay, for example, the VC dimension of linear models is related to the dimension of the space. Okay, and the second way in which PCA can help is it can identify which dimensions are irrelevant and identify which dimensions are important. The irrelevant dimensions mislead learning, and that's what leads to overfitting. And if you can throw away irrelevant dimensions, that's a huge bonus and a huge help to the learning. Okay, and then we'll touch on sort of other techniques, and you can read more about them in the literature, other textbooks, on what are called hints and invariances. So how do you incorporate known properties of a target function that may not be represented in the data? Okay, and another useful technique is having to do with deterministic noise and stochastic noise, which we studied when we studied overfitting. If you can remove those kinds of noise, okay, then you will overfit less. And so if you can remove detrimental data, it can only help. It typically helps the learning. So it's not the case that all data is good. If a particular data point is too complex or too noisy, you're better off removing it. Okay? And can we build techniques to remove detrimental data? I won't talk about that so much. You can read a little bit about it in the text. Okay. And lastly, there is a whole literature of research on better ways to validate. So we just talked about simple validation and cross-validation. But are there better ways to validate? Specifically, we use validation to do model selection in addition to estimating E-out. So if we can get better ways to validate, that can improve model selection. That gives us a better link from E in to E-out. Okay. Now, let's start with input preprocessing, and let's start with a little bit of motivation. Okay. So I'm going to invoke the nearest neighbor algorithm, this simple algorithm. It's simple, and we can illustrate the need for input preprocessing in this very simple example. Okay, so in this very simple example, you have Mr. Good and Mr. Bad, okay? And they were both given credit cards by the Bank of Learning. Okay, so it turns out, as you can expect, Mr. Good paid off the credit and Mr. Bad did not. Okay, so now here's the data. Okay, I'm showing you the age in years and income of Mr. Good and Mr. Bad. So age in years, 45 years, and income is in K, thousands of dollars. So income is 35K, and Mr. Bad, 22 years old, and income 40K. Okay, and so we can plot this data in the picture below. So you can see that Mr. Good paid off his credit. So his age is 47, and his income is 35K, and that's the blue circle. And Mr. Bad age is much lower, 22, okay, so closer to 20, and has a higher income of 40K, okay, and didn't pay, so that's an X. Now you've got Mr. Unknown who comes, okay, and we want to decide whether to give Mr. Unknown credit. Okay, so Mr. Unknown's coordinates are he's 21 years old, so 21, so very similar to Mr. Bad, and his income is 36K. So he's this black dot here. So his income is very similar to Mr. Good, but his age is very similar to Mr. Bad. Okay. Now I've plotted the data for you here, so I'm going to ask you to put on your nearest neighbor learning algorithm hat and tell me, should we approve the black dot? Should we approve Mr. Unknown or not? I'll give you 1, 2, 3, 4, 5 seconds while I take a poll. Okay, and it's clear. Okay, the nearest neighbor to Mr. Unknown, the black dot, is a red X. Okay. And so nearest neighbor says reject. Okay, great, fantastic. No problem here. And I'm now going to throw a wrench. Okay. The guy sitting next door to me, instead of measuring income in K, in thousands of dollars, measures it in dollars. So let's look at the same problem with the same people. Okay, except now the coordinates have changed. The data has changed. Okay, so Mr. Good is 47 and has income 35,000. Okay, not 35, okay, which was in units of K. and Mr. Bad is 22 with income of 40,000. Mr. Unknown has coordinates 21 and 36,000. So let's plot this data on a picture. Okay, now I have to choose axes so that distances are fairly represented, but you can assume that I'm not trying to play a visual hoax on you. I've plotted the data here, okay, and now blue, black, and red, as shown here. Okay, what's happened when I decide to measure income in dollars instead of thousands of dollars? Now, what I've done is I've emphasized the income as the important variable simply by changing the scale. Okay. And of course, you can go and do this experiment mathematically and compute the Euclidean distance to each of the data points from black to blue and red. And that's what I meant by, the visual here represents those Euclidean distances. Okay. And we ask you to put on your nearest neighbor hat again and tell me who is the nearest neighbor to black, and do you give or do you not give credit? And 1, 2, 3, 4, 5, all of you should say, well, now the nearest neighbor is blue, and the nearest neighbor algorithm says, give credit. Okay. Pause. There's a problem here, and this is a big problem. Okay. Same data, same Mr. Good and same Mr. Bad. Same unknown customer, okay, where all these people are just represented by their feature vector. Okay. The only thing that changed is the scale of one of the dimensions. Instead of measuring income in K, I chose to measure income now in dollars. And this is something that can arbitrarily be decided by whoever's collecting the data. They collect the data in K, or they collect the data in dollars. Okay. But depending on that scale, the outcome for the black Mr. Unknown is different. Okay, and then you try to explain this to the client and your boss. The boss says, well, but aren't the data sets the same in both cases, and aren't all the people involved the same? So why in one case are you rejecting and in the other case you are accepting? And the problem here is that scale does play a role in algorithms and in final hypotheses and learning algorithms. Not because it should, but just because it does, because most learning algorithms, okay, have a built-in scale. Okay. And what do I mean by that? What I mean by that is typically all algorithms that that we have sort of discussed in their default form treat all dimensions equally. Okay. And if, when you're collecting data, the scales of these different dimensions are wildly varying, then those different dimensions with wildly different scales will be emphasized differently by the algorithms. Now, if that is by design, then fine. If you really think that income should be twice as important as age, then fine, if income has a scale that's twice as large as age. But if it isn't, and this is typically the case, that by accident, the person who's collecting the data just decides I'm going to, report the data in dollars instead of thousands of dollars. If this scale occurs by accident, by just some arbitrary choice, it should not affect the outcome of the learning. Okay. So the goal when we do input preprocessing is to sort of preprocess the data so that arbitrary choices like scale do not affect the outcome. Okay. Now, if you want to be a little bit more quantitative and understand why scale is so important, you can look at, how some of the algorithms work. So let's talk about nearest neighbor. So nearest neighbor. Okay. We implicitly define the distance, okay, between x and x prime as the Euclidean norm of the difference between x and x prime. Okay. So where's scale here? You see, the Euclidean norm treats every dimension equally. Okay. And if you have an arbitrary scale in one of the dimensions, now that dimension can be either underpronounced or overpronounced. Let's look at weight decay. Weight decay is lambda W transpose W. Okay. It treats every dimension equally. The support vector machine margin is defined using Euclidean distance, okay, which treats every dimension equally. The RBF bump function is defined using the Euclidean distance as the similarity measure. Okay. So this is just to illustrate that any machine learning algorithm in its default state, typically treats the input dimensions equally. So when you use such an algorithm, you have to make it so that the input data does indeed represent each dimension equally. And if it doesn't, it should be by design, not by accident, not by the arbitrary choices made by the person collecting the data. Okay. So unless you want to emphasize certain dimensions, the data should be pre-processed so that it presents each dimension on an equal footing to the algorithm, because the algorithm is expecting that. The algorithm operates on that assumption. Okay? And so with that, let's talk about some basic pre-processing, transforms of the data, basic input pre-processing. And then we'll talk about PCA, which is a slightly more sophisticated input pre-processing. Okay. So what's the idea behind input pre-processing? So you have your data matrix X, whose rows are X1 transpose, X2 transpose, and up to Xn transpose. Okay. So, and what is an input pre-processing? Basically what we do is we take each data point, X1, X2 up to Xn, and transform it into Z1, Z2 up to Zn. Okay. So we've seen transforms before. We've seen the nonlinear transform before. No different here, except that the goal is different. Okay. Here we're not doing any fitting. We're not looking at any Y values, nothing. Okay. There the goal was to address E in. Here we're just trying to put the data into some normal format. Okay. And, this transform from Xn to Zn is going to be implemented by a function, by an input pre-processing function, phi, just like in the nonlinear transform. And, you do your learning with the Z's. Okay. And now when you want to compute your final hypothesis for the raw original input, so you want to compute G of X, okay, you first transform the data to phi of X and implement the learned hypothesis on the transformed data. So this is no different from what we did when we talked about nonlinear feature transforms. Okay. And we're going to now design input pre-processing transforms that, will, for example, take your raw Xn, which might have arbitrary scalings in each dimension, and produce Zns, which will not. Okay. So let's start with three very basic transforms. Okay. They come at almost no cost, very easy to implement, and so you should implement them because it puts the data into this, standard format. Okay. Since the algorithms are expecting this, you'll get a lot of benefit by just systematically always input pre-processing the data into this standardized forms. Okay. The first is centering. Okay. So imagine that your raw data X, I'm just showing two dimensions, but imagine that your raw data, X1 up to two-dimensional X1 and X2, and I'm showing the blue dots. Okay. Centering, very simple. Shift the data. Okay. Shift the data so that, the center of the data aligns with the origin. Okay. And I'm showing on the right, an example of, well, not an example, but for this data, what would the centered data look like? You just, you shift every data point. So Zn is just the corresponding Xn. So the transformed data point is the corresponding Xn minus the average data point. Very easy to implement. Okay. And notice that this is a reversible transform. So given the Zn, you can, as long as you remembered the mean X bar, you can recover the Xn. So there's no information loss. Now, if you look at the original data, the raw data, you'll see that, they're off center. What that means is that the average data point is not at the origin, but for the transformed data, the average data point by construction will be 0, okay, because the average of Zn is the average of Xn minus the average of Xn, minus the average X, which is the average of Xn. So that's 0 minus, that is average minus average, which gives you 0. Okay, and this is a very easy transform. Basically no downside. So from now on, we will assume that we've centered the data. What's the next thing you can do? Well, what I'm showing in this blue data here, you can see that the scale of the, X1 dimension seems to be smaller than the scale of the X2 dimension. Okay? And that also is preserved in the centered data. So the scale of the Z1 dimension is different from the scale of the Z2 dimension. Okay? So the next input transform after you have centered is to rescale. Okay? So this is called normalizing the data. So what have we done? We have multiplied the Z1 dimension by a constant and multiplied the Z2 dimension by a constant, okay, and that effectively rescales each dimension independently, okay, so that now the spread in each dimension is roughly the same. Now there are many ways to normalize. You can normalize in terms of a min-max range. So you might want the min to be -1 and the max to be +1 in every dimension. This is something you explored in one of the assignments. A more typical way of renormalizing is to ensure that the variance in each dimension independently is 1. Okay? And that corresponds to scaling each dimension by the inverse of the standard deviation of that dimension's data. Okay? So this corresponds to taking Zn and multiplying by a matrix D, corresponds to taking Xn, multiplying by a matrix D, okay, to produce the transformed vector Zn. okay, where this matrix D is a diagonal matrix, okay, and all the diagonal entry DII is 1 over the standard deviation for the corresponding dimension, so 1 over sigma I. Okay. After you have transformed in this way, after you have normalized, after you have rescaled each dimension, if you compute the variance of the z's in each dimension, you'll find that the variance is 1. So I won't go through that little derivation. It's very easy for you to convince yourself. Okay. Last example of a simple transform, whitening. Okay. Now, look at the difference here. Now, whitening, so again, normalizing, very easy to do, and almost no reason not to do it. So it now puts all the data, all the dimensions on the same scale, and that's perfect for weight decay, perfect for, Euclidean distance, and so on and so forth. And again, this is a reversible transform, so there's no information lost. As long as you remember the matrix D that performed this transform. Now let's talk about whitening. Okay, so what's the difference? So we've now rescaled the data. You'll observe that this data is not sort of spherically symmetric. So basically what whitening does is it makes the data spherically symmetric. Now this transform is not necessarily always done. So raw data centering, almost no reason not to do it. Normalize, almost no reason not to do it. Well, in some situations you may not do it. Okay? If you believe that the dimensions that were chosen were not arbitrary, then you don't want to normalize it. But whoever is in charge of collecting the data has made a design choice that yes, Z2 should be twice. Okay, so you have to think a little bit about normalizing. Centering, always do it. Okay, and now whitening essentially makes the dimensions independent. So it takes this sort of correlated data and produces uncorrelated data. And so that's what's called a whitening transform. So if you look at the variance covariance matrix of the normalized data, okay, let's call that sigma. So sigma is the sum of the outer products, the average of the outer products. It's equal to 1 over n times the data matrix transpose times the data matrix. Okay, so you can work all these details out. Why is it the sum of the outer products, not the sum of the outer products minus the outer product of the means? Is because we've assumed that you've centered, so the mean is 0. Okay, and so if you take your original data multiplied by the sigma to the minus 1/2, okay, now what is the definition of sigma to the minus 1/2? So sigma to the minus 1/2 times sigma to the minus 1/2 is supposed to be the inverse of sigma. Okay. And we will quickly prove once we get to the board that this whitening transform actually does whiten the data. What does that mean? So once you perform this whitening transform, the covariance matrix for the transformed data will be the identity. So normalizing, what did it accomplish? It set the variance of each dimension independently to 1. But there could be covariance between Z1 and Z2. Once you whiten, you not only have the variance along each individual dimension equal to 1, but the covariance between any pair of dimensions is now 0. Okay. So the covariance matrix of the transformed data is basically the identity. And I'll leave it as an exercise for you to prove that if you implement this transform on the raw data xn and compute z the sum of the outer products for z of z and zn transpose, okay, the sum of those outer products, you will find that you get a sigma that cancels out the sigma inverse, and so you will get the identity. Okay, I leave that as an exercise. So raw data, nothing to lose by centering. Okay, always do it. You have centered data. Now you typically always want to normalize, unless the person who collected the data said, don't normalize because this dimension is twice as important as that dimension and its scale is twice as large as that scale, and I want it to stay that way. Okay. Otherwise, you'll typically always normalize. And then whitening not only normalizes but also decorrelates. Okay. Now, whitening is not necessarily something that everyone always does, but it can be useful if you're not going to do anything more sophisticated afterwards. So then, once you whiten data, these dimensions can be treated independently. If you don't whiten data, and let's say you do a linear model and it has a weight W, 1 on Z1 and 1 on Z2, well, those are correlated dimensions, so you don't really know, how important is the variable Z1. What happens if the weight on Z1 was close to 0 and the weight on Z2 was large? Well, because Z2 and Z1 are correlated, there's the fact that Z2 has a large weight is kind of indicating that Z1 has some role to play because Z1 is related to Z2. Okay. And it's typically the case that when variables are correlated, it's easier to overfit. Okay. And when variables are independent, it's typically harder to overfit. Okay. If there's going to be less overfitting. So you can read the text for more detail. Okay. So simple transforms that are easy to implement and usually no downside. Okay. Now, hidden danger, especially with things like normalizing, whitening, and so on, centering, and so on. Okay. Warning. Okay. So you're taking your data, you're choosing a transform. So in all these cases, look, the transform to Zn involves, looking at the data. Your transform, because the mean of the data involves the data. Your transform to Zn involves the standard deviations along the various dimensions. So that means you have to look at the data. And in whitening, you're really looking at the data because you need to compute the covariance matrix for the data points. And then you're going to transform using that covariance matrix. So you have to look at the data. So all the input processing, pre-processing transforms look at the data. Now, if you're going to look at the data, you had better make sure you're only looking at the training data. Otherwise, you're data snooping. So if you've set aside a test set, but you did your let's say normalization before setting aside the test set. So you choose the scales of the data using all the data, then you set aside a test set, you have data snooped. Because properties of the test data have affected the training data, which will then affect the final hypothesis. And if a data set affects the final hypothesis, you cannot use that data set to evaluate the final hypothesis without taking into account that data snooping. So, as a rule, first create your test data the moment you see the data. So the moment you get the data, lock it in a vault, your test data. Now, okay, so that means that you split your data into the test set, which is in a vault, and your training set, where you can do input pre-processing, as much as you want at will. Okay, do centering, do normalizing, construct your input pre-processing function phi. Okay, construct your pre-processed data z. Okay, do your learning. Okay, get your G-tailed. Now open the vault. Okay, get your test data and apply G-tailed, which was learned on the Z, to the transformed test data. Okay, and that gives you a test set. And only then is your test set an unbiased and unsnooped estimate of the test performance of G-tailed or your final hypothesis G. And on the right, I'm showing you an example where all we did in the text is a little bit of data snooping to decide, the mean vector for centering, in the centering input pre-processing step. Okay. And in finance, if you do any kind of data snooping, it's devastating. Okay. Because the mean of the test set tells you, in some sense, whether the test set is high or low. And so if you use that to predict your trading strategy, you make a lot of money. That's the red curve. Okay. And without snooping, you don't make any money. Now, if you think that you're going to make a lot of money because you snooped, and then you put a lot of money on trading in the test deployment phase, what you'll actually experience is the non-snooped version. So you have just conned yourself. Okay. So, warning. Transforming data into a more convenient format has this hidden trap which leads to data snooping. Very often people, do the normalizing and then say, oh, you know what, I need to have a test set. And many of you have already recognized on one of the assignments that we implemented this kind of data snooping. Many of you found this out. Many of you even corrected it. Okay. This is one of the most subtle forms of data snooping, is when you do input pre-processing before you set aside your test set. Don't do it. Okay. Now, let's go to the board. I'm going to tell you about this powerful technique called PCA. And it's a very powerful technique. It's a very commonly used technique, and there are even nonlinear versions of it, but we're going to discuss the linear version of it. So we're going to discuss linear PCA, principal component analysis. Okay, so before we talk about PCA, let me just mention that all the input pre-processing techniques that we've discussed, and the same holds with PCA, were unsupervised. Nowhere did the Y values, the target values, make any appearance. Okay. Now, some people use this as an excuse to say that, that kind of data snooping where you do your pre-processing including the test set because that's more convenient. They say, oh, so that's a mild data snooping because we're not looking at the Y values. Well, it's data snooping nonetheless. Okay. Now, yes, typically when you data snoop and also look at the Y values, it's going to be a total disaster. But why should you data snoop at all? Okay. Don't do it. Why con yourself? You don't have to, so don't do it. Don't data snoop in any way. Okay, now we're going to talk about principal component analysis. Okay, and I've taken the liberty of drawing that data that we had. Okay, and you'll observe that I've assumed that the data is centered. So that's always the case when we're doing principal component analysis. Now, if you need to be able to reconstruct the original data, then you need to store the mean shift that has occurred, the center shift. Okay. Is the data normalized or not? Well, that depends. If the domain expert collected the data carefully and the scale of the various dimensions is important, and the domain expert tells you that, then you don't rescale, you don't renormalize the data. Okay. So renormalize or not, that depends on what the domain expert told you. On the other hand, typically the case, the domain expert is agnostic. No, I just collected the data. How did you collect income? Oh, in cents. Oh, is that important? Oh, no, I just collected it in cents. How did you collect the temperature? In Fahrenheit. Oh, not Celsius? No, not Celsius. Fahrenheit. Oh, is that important? No. You see, so these are the kinds of things that the expert might say, I don't care. So you do what needs to be done. So they don't care about the scale. But if they do care about the scale, you don't normalize. Okay, now whitening. You don't whiten the data if you're going to do a principal component analysis. If you whiten the data, there's nothing more for principal component analysis to do. So principal component analysis is geared for data that looks like this, where the dimensions seem to be correlated with each other, and it untangles this correlation in a meaningful way. If you whiten the data, all the dimensions become mutually independent, and there's nothing for principal component analysis to do. So data is centered, normalized or not depends on what the domain expert told you about the relevance of or how the scales were set. Whitening, no, you don't whiten before PCA. Okay. Now, let me talk a little bit about the motivation of PCA. So when you look at this data that's been centered, you will observe that I've measured x1 and x2. Okay, but it looks like I have not measured the right axes for x1 and x2. Those are the wrong sort of measurements. It would have been sort of much nicer if I had measured, if I defined this as my axis and that as my axis, and then I told you, what's the coordinate in this axis and what's the coordinate in that axis. So those seem to be the natural axes for this data. Okay. And if you view this data through these two natural axes, okay, then the data looks much nicer. Okay. Through these natural axes, so let me call this natural axis, a V1, and this natural axis a V2. Okay. Then the data looks much nicer. Okay. So if this is now V1 and this is now V2, okay, then the data is much nicer. It looks like this. Okay. And when I see the data in this form, I immediately start thinking, the second dimension looks useless. It's small, looks like small random noise. Okay. So the second dimension looks like small random noise. Okay, because it's just small variations, and the major action is going on in this first dimension. Okay. And sometimes we will say, well, this first dimension V1 is the dominant direction for this data, and then the minor directions are, for example, this V2, and we're not interested in the data dimension V2. Okay. So how does that help us? So we started with x is equal to x1, x2. You can think of those as the coordinates of x, okay, along a basis, an orthogonal basis, which is composed of the standard Euclidean basis vectors, e1, e2. Okay, and how is this? How are the coordinates x1 and x2 defined? Well, they are defined as x dotted into, okay, so x transpose E1 and X transpose E2. Okay? And the standard Euclidean basis is what gives us our standard coordinates for X. Okay? But we're arguing that the standard Euclidean basis giving us the standard coordinates is not the natural basis for this data. The natural basis for this data is V1, V2. Okay? So if viewed from the natural basis for this data, so then the coordinates of x in this natural basis, so the coordinates of x in the natural basis, so let's get the coordinates of x in the natural basis. So that would be X transpose V1. So assuming that, this natural basis is an orthogonal basis, X transpose V1, X transpose V2. Okay. So if I could figure out what's the natural basis, I can get the coordinates in this natural basis, and I can call these coordinates, I can call them Z1 and Z2. Okay. And you see what I've accomplished. What I've accomplished is I've taken my X, okay, which is X1, X2, in my standard Euclidean basis, okay, my standard Euclidean basis E1, E2, and I've converted it into Z1, Z2 in the natural basis V1, V2, okay, and this is the transformed vector Z. Now, as long as this basis V1, V2 is an orthogonal basis, there's no information lost here. It's basically a rotation of the data. And as long as you store the rotation, as long as you store the V1, V2, you can recover X from V1, V2. So, as long as you recover, you can recover. So you can write X is equal to X1, E1 plus X2, E2. It's also equal to Z1, V1 plus Z2, V2. So as long as you know the basis, V1, V2. In other words, you know the rotation, you can recover the vector X. Okay. But for the moment, it's not that important for us that this is an invertible, this is a no information loss transform from X to Z that is captured by just a rotation of axes. Okay. Because one of the whole points of PCA is to actually now start throwing away dimensions. Okay. In other words, that reduces the dimension, okay, making the link from E in to E out, let's say, tighter for linear models. But also the idea is that not only are we going to reduce the dimension, but the dimensions that we're going to throw away are supposed to correspond to useless noise, random, small, noisy variations, stochastic noise that, and perhaps even some deterministic noise that we don't want to have in the data, which will lead the learning astray. Okay? So how is that accomplished? Well, you can't throw any of the dimensions x1 or x2 away. You can't throw x1 or x2 away because look, if you throw x1, you're throwing a big part of the vector. But when you look here, you can see, now if I throw away the v2 dimension, if I throw away the coordinate z2, I haven't lost that much information because now I'm going to now go from z1, z2 back and throw away z2 and get the transform from x, which is x1, x2, to just z1. Okay. And now let's see what we have accomplished. Oh, we've taken x1, x2, a two-dimensional vector, and produced a one-dimensional vector z. Okay. And the component z1 is just the projection of x onto the dominant direction of v. Now this step loses information. I can no longer reconstruct x from z. I can say that x is approximately equal to z1 times v1. Okay. But the term that I've left out the term, plus z2 v2. Okay, so this is the term that I've left out. But the idea is that it's still a good approximation to x. Why? Because the term that I've left out in approximating x by construction is small, because that's why I threw that term away, because the value of z2 is small compared to the value of z1, the projection on the v1 axis. And so that's the value, that's the use of putting the data into this more natural set of axes. It instantly identifies for us what's the useless dimension, the dimension such that if I threw it away, I haven't thrown away much information, at least from the perspective of reconstructing x. Okay. And that is the philosophy of principal component analysis. Step 1, identify the dominant directions. Step 2, throw away the small dimensions. Throw away the small dimensions. Okay, and this does two things. One, dimensionality reduction. That's what it's called. Dimensionality reduction. 2, It throws away, presumably, small, deterministic or stochastic noise. So irrelevant dimension. So the information thrown away is irrelevant. Throws away irrelevant info. Okay. Now, dimensionality reduction, that's a given. If I throw away the Z2 dimension, I've reduced the dimension. This is always. This is a hope. So the hope is that the information that you're throwing away, at least with respect to being able to reconstruct X, that's useless, irrelevant, noisy, stochastic, and deterministic noise. So we don't need it. In fact, it might even be better to throw it away. It cannot lead the learning astray. Okay. And so PCA is an algorithm that does this. Okay. And the first step is to identify the dominant directions. But before we go into the algorithm and derive it, it's not going to take us too long to derive. Let's see what's the main flaw. Okay. The main flaw with PCA, and people have tried to address this by doing what's mildly supervised PCA. The main flaw with PCA is it's unsupervised. Okay. So why is this a flaw? Okay, so let's think about it. We've thrown away a dimension. So now let's take an example. Height. Okay. Height is varying a lot among people. So it's the dominant dimension. Blood sugar, or A1C. So that's, typically within a small range because, humans, the general way in which the human body functions is what's called using, homeostatic mechanisms. So things are kept at a stable level. So typically your A1C is at a stable level. And if it deviates a little bit from this stable level, then that could indicate diabetes or some kind of, other disease. Okay. So A1C might be that. And if we're trying to predict diabetes, the only thing that matters is your A1C, not your height. And we've just gone and thrown it away because it's a minor dimension. Okay. So the flaw with this process, and this is why this is a hope, the flaw is, so the flaw is that the small dimension we throw away contains all the useful info. And that was a disaster. Messed up. Okay. And the learning is going to completely fail. And now I'm going to come and say, okay, well, if this is indeed the situation you're in, you were doomed from the start. Okay. So, let's see why. So you've thrown away, well, first of all, if you implemented this process and threw away this small dimension and it contains all the information you need to predict diabetes, then you're done for sure. You're done. Okay. So, let's consider the competing alternative. You kept that data point. You kept that dimension. So let's see what you kept. You kept the informative small piece of the informative small dimension. But by definition, that's the small dimension. That's the signal is small. And so what is this other dimension doing here? This must be just irrelevant information. This must be noise. So if you don't throw that information away, okay, you're done. If you throw that information away, you're done. If you keep that information, well, you're basically done because your signal to noise ratio is basically 0. So you're done anyway. You're done in this problem because your signal to noise ratio is minute. You have too much noise. And you would need a very sophisticated approach which could somehow be able to identify a small signal inside a huge noise. So in some sense, this hope is kind of a without loss of generality. If this hope is not true, you are doomed anyway. So you're doomed if you do, doomed if you don't. Okay. So we might as well assume that, the hope comes true and see what we can accomplish. Because if the hope is not coming true, you're doomed anyway. So you'll figure out that you're doomed and, E in is close to E out, you'll say that, or you'll have a link to E out, you'll say E out is bad, you're done, you failed. Okay. So let's at least consider the situation where signal is much larger than noise, in which case this hope can be fulfilled. Okay? And let's talk about now the algorithm that does that. Okay. So the idea, let's call this direction now V. Okay. And for the moment, we won't need the second direction. So let's call this dominant direction V. So call the dominant direction V. So the data, when projected, in this basis, but let's look first at the coordinate in the dominant direction. So the coordinate Z in the dimension that corresponds to V is exactly X transpose V. So Z is equal to X transpose V. Okay? And, what would it mean for this direction to be dominant? It means that it has the large variances. Now, since the mean is 0, the large variance in that dimension basically means that the square of, the value, the square of this coordinate has the largest, in some sense, average value. So we will define Z as the dominant direction if it has the largest variance. The variance is measuring this spread. So we want this spread to be large, or this spread to be large. That's what makes it the dominant direction. Okay? And in the minor directions, the spread is small. Okay? So in other words, the average squared value, so the sum, let's call it the sum over your data points, because these are your data points, the sum over your data points going from 1 to n of the squared value, Zn squared, is as large as possible. Now this is the variance because the mean is 0. So when the mean is 0, the variance is given by the average squared value. Okay? So let's look at, so let's try to find the direction V that gives us the largest average squared value. So what direction V gives the largest squared coordinate on average? Okay, so let's look at Zn squared. So Zn squared is equal to xn squared, the nth data point. So the z coordinate for the nth data point is the xn squared dotted into xn transpose v. So that's the coordinate squared. Okay. So this is equal to the square of some number is equal to its transpose times itself. So a vector, a number squared, okay, can be written as x, times x, which can be written as x transpose x. Okay. So this number squared can be written as v transpose xn transpose v. Okay, so here's the number transpose. Here's the number. Okay, so the number transpose times itself. Well, in this case, both of these are numbers, so this is Zn squared. Okay. So now, what we would like to do is we would like to find the direction V which maximizes this on average. So let's see what the average is. So 1 over n, the sum from n equals 1 to big N of Zn squared is equal to the sum over n, 1 over n. So the sum over little n going from 1 to big N. Okay, V transpose xn transpose V, which is, now V is a constant, so we can pull it out of the summation. So this is 1 over n, V transpose the sum from n equals 1 to big N, xn transpose times V. So I pull the V, which is a constant, outside. I'd like to pull this guy also outside, but because these are vectors, I have to preserve the order. I cannot, mess around with the order. So I can pull this guy outside the sum on that side. I can pull this guy outside the sum on this side. Okay, and I'm almost done. Let me take this n inside the parentheses here. So this is equal to V transpose 1 over n, the sum from n equals 1 to big N, xn transpose times V. Okay. And this is a very famous matrix associated with the data. This is called the covariance matrix of the data. Now, the reason that this is the expression for the covariance matrix of this data is because it has already been centered. Otherwise, to get the covariance matrix, you would subtract the mean vector times the mean vector transpose. Okay, but in this case, the mean vector is 0 because it's centered. Okay, so this is equal to V transpose sigma of V, where sigma is the covariance matrix of the data. This is a positive semi-definite matrix. It's typically just positive definite. So, the direction V that gives the largest squared coordinate on average is the direction V that maximizes this quantity. So we have solved our baby problem. This direction V that gives us the largest squared coordinate on average, the largest spread in that direction, is the direction that maximizes, so V maximizes V transpose sigma of V. Okay. So we need to find the direction V, the unit, a direction is a unit vector, so we need to find the direction V that maximizes this quadratic form where this is a positive definite covariance matrix, and we know how to solve that problem. This is a purely linear algebraic problem, okay? And the solution is to look at the eigenvectors and eigenvalues of sigma. So let the covariance matrix have eigenvectors v1, v2, v3 up to v sub d. So if the data is d-dimensional, the covariance matrix is a d by d matrix, and so there'll be d eigenvectors and corresponding eigenvalues ranked in order of size. Okay, and eigenvalues lambda 1 greater equal to lambda 2 greater equal to lambda 3 greater equal to greater equal to lambda d, and because this is positive definite in the typical case, this is greater than 0. Okay, then the V that maximizes this quadratic form is exactly V1, and V star is equal to V1. And in fact, okay, the dimensions in order of decreasing importance are exactly V1, V2, V3 up to V sub d. And the basis that rotates the data into this form is exactly the orthogonal basis V1, V2, V3 up to V sub d. Now, some properties of sigma are that it's positive, definite, and symmetric. That means that these eigenvalues are all positive, and it's possible to choose these eigenvectors as orthogonal. So these are indeed a basis. Okay. So there, we've gotten the dominant direction. Okay. So, algorithm, very simple algorithm. Okay, and it comes to us from linear algebra. Step 1. Find sigma and eigenvectors v1, v2 up to v sub d. Sigma comes from the data. It's the covariance matrix of the data. And these are in order of decreasing eigenvalues. So lambda 1, lambda 2, lambda sub d. The dominant direction is V1. And so this is an orthonormal basis. In fact, you can take all of these vectors as your basis for your rotation and as defining a new coordinate system, and we can define z equals x transpose v1, x transpose v2, x transpose v3, x transpose v sub d, which is the coordinates of z in this basis v1 to v sub d. And we just proved that this guy gives me the maximum variance. Well, it turns out that this guy gives me the next maximum variance if I restrict myself to directions that are orthogonal to v1. Okay. And then this guy gives me the next maximum variance. So these are directions of decreasing variance, but they are optimal. So this is maximum variance, max variance. So maximum spread, and we just proved that. And that's the definition. In fact, it's now easy to show that, if you use the eigenvector with the maximum eigenvalue, well, then this product will be exactly lambda 1 squared, and you cannot get better than lambda 1 squared for this product. Okay. So this is maximum variance. This is max variance constrained to being an orthogonal direction for orthogonal to V1. And then this is the max variance for orthogonal to V1, V2, and so on. Okay, so these are the directions in which you capture the most variance of the data. Okay. Now, there's a theorem of Eckert-Young. So what we're going to do now is we're going to construct these coordinates, and in this example there are just two, and then we're going to decide on a threshold and say, you know, beyond this value, these spreads are so small, that's just noise, and we throw those away, and then Z1, Z2, Z3, and so then we achieve dimension reduction, plus we've thrown away the irrelevant data. Okay. So the algorithm is find the dominant directions and then decide, you know, how many coordinates to keep. For example, K. And then what we call these are the top K PCA coordinates, or the top K PCA directions. So this is called top K PCA, principal component analysis directions. Okay, so you throw, we just, and that's the whole goal. We've identified the directions in which the variation of the data is small, likely to be noise. Okay. Identify those directions, throw them away. Now, how do you pick K? Typically, you know, what you do is you look at how the size of each of these dimensions, the size of each of these coordinates on average, and once the size gets smaller than some threshold, or once you've captured, you know, a lot of the variation in these coordinates, once you've captured enough variation here, you throw away the remaining. Okay. So very often the choice of K is based on the nature of these variances. Okay. The nature of how much the spread is here. Okay. So you capture a certain amount of spread, you capture a certain amount of spread, and so on and so forth. So in other words, you are able to reconstruct X. So you reconstruct X. So X gets reconstructed as Z1, V1 plus Z2, V2 plus all the way to Z K, VK. If you're doing top K PCA, so X is approximately this guy. And so there's an error made, okay? And you keep putting in components until the error made on average is small enough. Okay. It's possible to show that if you're given K directions, the top K principal component directions are the ones that give you the smallest reconstruction error. So the top K PCA directions give the smallest reconstruction error. This is called the Eckert-Young theorem. Okay, but that's not so. You can see the proof of all this in the text. The idea, the motivation is that, you know, we want to rotate the data so that it becomes obvious what the small directions are. And once we know what the small directions are, we treat them as noise and throw them away. And how does it become obvious? So when you do when you find the PCAs, okay, the bottom principal component is the smallest direction. Throw it away. The next is the next smallest. Throw it away. And keep throwing away directions until you feel like you're throwing away too much reconstruction capability, at which point you stop and you identify K. Okay? And when you have done that, you have performed a dimensionality reduction to K features. Those are sometimes called the top K principal component features. So the top K PCA features. Okay. And now let's go and see some pictures of how the top K PCA features behave, how they perform when it comes to the digits data. Okay, so just a quick recap of what we just discussed. The principal component analysis algorithm. You construct your top eigenvector of your covariance matrix. That gives you the first coordinate of your transformed data point. The second eigenvector gives you the second coordinate. The third eigenvector gives you the third coordinate. And at some point you truncate and you say, I've collected my dominant directions and the rest are noise. Okay? And that gives you dimensionality reduction. And also presumably you've thrown away the small variations that correspond to irrelevant or noisy, data. Okay. And now let me show you what happens if I just keep the first two PCA directions with the digits data. Okay. Wow. Okay. So PCA direction 1, Z1, PCA direction 2, Z2, and 1 versus not 1. You see how nicely separated they are? That's because in this particular instance, the dominant directions in my data actually are the directions in which most of the information lies, and you could nicely separate 1 from not 1. Okay. And on the left, I'm showing you, how the reconstruction error. Remember, we can use the principal components when we multiply by the corresponding vectors, we get a reconstruction of x. So how does the reconstruction error drop with k? And the percentage reconstruction error, so we have 216 or so features. The percentage reconstruction error drops to below 10% with about, drops to about 10% with about 50 PCA features. And so sometimes the 90% reconstruction capability is the choice for k. So we can easily drop down to 10 to 50 dimensions, and the remaining 150 or so dimensions containing, nonsense. And so, we could in this way construct 50 dimensions and probably get pretty good performance on the digits data. But what I'm showing you here is just 2 dimensions. Now let me briefly talk about other learning aids. So PCA is linear dimensionality reduction. So, and on the top left, I'm showing you data that's clearly one-dimensional, but it's a spiral, so it's not linear. If you try to construct a linear dimension to capture the data, you'll see that it doesn't capture the data, that it cannot reconstruct the data. The data doesn't lie, on a linear one-dimensional surface. But if you give me a nonlinear capability for dimensionality reduction, then I can capture the data well. And what would be my dimension? It would be the distance along this red curve. That would be my feature. And that captures the data quite well. And then the variations of this red manifold that's nonlinear could be treated as noise. Whereas that's not the case if you try to do a linear dimensionality reduction. So PCA would not work with this data. Okay. Now, we're not going to talk about nonlinear dimensionality reduction. You can read about it a little bit in the text and, in the literature. Sometimes you have information about the function like, it's rotationally invariant, especially in vision, or monotonicity. So whether or not you get credit should be monotonically increasing in your income, or symmetry. Okay. If something happens when you got richer, then the opposite should happen when you got poorer. So that's an example of symmetry. Okay. So those are called invariances and prior information that you have about the target function, and there are methods for incorporating those into the learning. Now, why would you need to? Because those invariances, for example, rotational invariance, might not be embedded in the data. So you'll see a picture of a tree. The data may not contain the fact that the rotated version is a tree, or the rotated version this way is a tree. But what you can do is you can add those invariant versions and also label them as trees because you know that the target function is rotationally invariant. So that allows you in some sense to augment the data. Those are called virtual examples. Okay? But you can read more about hints. Another perhaps useful task, or if we could do it, is to remove noisy data. So I'm showing on the left the digits data, and you can see some hard examples that have been identified by a very simple algorithm that tries to identify noisy or difficult data. Noisy could either be stochastic noise or deterministic noise. Now, so this blue circle in the middle of all this red could be treated as stochastic noise. That's just mislabeled. Okay. But then there's a lot of deterministic noise that was identified, by these boxed data points, and you can see that it may not be that they're mislabeled; they're just very hard, for this two-dimensional feature set and a linear model, let's say. Okay. So if we could remove this detrimental data, noisy data, then we can get separate the classification boundary on the right. Whereas if you kept it, you get the overfit version on the left. Okay, so removing detrimental data can be useful, but we're not going to cover it. I just, mentioning it to you. Advanced techniques. Okay, there are lots of advanced techniques, especially for estimating E out. Some of them are more efficient than cross-validation. Some of them are better than cross-validation in terms of convergence properties. Okay, and so you can read about it in the text. Okay, so there's a lot that can be said about learning aids. Okay, and learning aids are techniques that can be used to help any learning model, any other technique that we have. And so what we covered was input preprocessing. Do it. PCA can be useful if you really need to lower the dimension while keeping what should be the important relevant data and throwing away the unimportant small variations, noisy data. Okay, but there are other techniques like nonlinear dimensionality reduction, invariances and prior information hints, removing the noisy data, advanced validation techniques, lots of stuff that can help learning no matter what model you use. And with that, we're checking out.